As I began mentioning in the beginning of Chapter 9, there's not a significant difference between a trap routine and a user subroutine. Trap routines are subroutines that live in system space, and they have a special or an additional step in calling the system subroutine in the form of the trap vector table, holding the address of the first instruction of the system subroutine. So now we're going to move into user subroutines. Let's get started. A little bit of review here in that service routines, system subroutines that live in system space, provide three main functions. They shield programmers from system-specific details in the form of abstraction. They write frequently used code just once, mostly I/O routines. And they protect system resources from unintended programmer mistakes or malicious programmer intents. So we have the same functionality for non-system code in the form of subroutines, which is the topic of this entire lecture. So a subroutine is, or can be looked at as a function. It's a fragment of code that is defined or lives in user space and performs a specific task. So if we're talking about top-down design or stepwise refinement, you break your program into subtasks. You can implement subtasks as a subroutine. And the subroutine is called by either your main program, or it could be called by another subroutine, and it performs the task, then returns control to the calling program when it's finished. It's just like a service routine, but it's not part of the operating system, so we're not concerned with protecting any specific system resources or hardware resources. We're not worried about special privileges. This is just code that is reused over and over. So, you know, if you have code that you're going to call multiple times and you don't want to keep coding it, you could implement it as a subroutine. If you are dividing tasks among multiple programmers in a stepwise refinement or top-down design scheme, you could assign specific subroutines to one or more programmers in a team. And you could also implement vendor-supplied libraries of useful subroutines. So none of this should be new information for you. This is all review of topics you've covered in previous classes using high-level programming languages. So the context is just a little bit different. Here we have the three instructions we're going to use to implement subroutines. They are JSR, JSRR, and return. And return is really a jump bar 7, a hard-coded jump bar 7. JSR uses a PC offset, an 11-bit 2's complement, sign extended, you know the routine, sign extended to 16-bit offset to identify the target address which holds the starting instruction, the first instruction in the subroutine. We also have JSRR, which requires the use of a base address to hold, base register to hold the address of the first instruction of the subroutine. And as you would as you would imagine, that requires us to use a base register, but it has no leash. There is no limit to how far the subroutine code can be from the JSR, the jump to subroutine command. And once again, return provides a linkage back to the calling routine. It's a jump R7. R7 holds the contents of the program counter as moved during the JSR, just like a trap routine. So if you've got a JSR command instruction on at hex 3003, when you execute the JSR, the program counter will have been incremented to 3004, and that'll be stored into R7. So when your subroutine comes to the return, i.e. jump R7, it will go back to 3004, the value in R7. Of course, if your subroutine utilizes R7, you need to save R7, preserve it, and then restore it before the return, or you will have broken the linkage back to the program that called the subroutine. Here we have the JSR command in its 16-bit syntax. The opcode for JSR is 0100. Bit 11 is always a 1. And PC offset 11. So it jumps to a location, just like a branch, but it's not conditional. And it saves the program counter automatically in R7, which is the linkage. And the target address is the PC program counter plus the sign extended 11 bits in bit 0 through 10. And that gets added to the program counter. And so you've got a leash. Okay, I can't remember right off the top of my head what the range is of an 11-bit 2's complement value, but it's finite. Here's a diagram of the micro instruction. First step is the program counter gets written to R7. Then the program counter is passed as the first operand to the arithmetic logic unit, and then the arithmetic logic unit gets the instruction register sign extends bit 0 to 10 to 16 bits, and that gets added to the program counter value, and then the arithmetic logic unit writes the new program counter, the new value to the program counter. Pretty straightforward. JSRR uses the same opcode as JSR, except bit 11 is a 0 for JSRR and a 1 for JSR. And we have bits 6, 7, and 8 hold the address of a base register, which holds a full 16-bit address for the first instruction in your subroutine. This question, what important feature does JSRR provide that JSR does not? I think I've already answered that, but just for the sake of it having it on the slide, JSRR does not have a leash. There is no limitation as to how far away from the call, the jump to subroutine call, that the subroutine can be. So, as I've mentioned a few different ways already, the JSRR, jump to subroutine register mode, computes the address, the starting address of the subroutine differently. The subroutine is specified by the contents of the base register, bits 6, 7, and 8 of the instruction. So, as I've already said at least 2 times, probably 3, the major advantage of JSRR is that it's unlimited as to where the subroutine can start. It's not restricted to the range of an 11-bit 2's complement offset. And the micro instruction for JSRR is a lot simpler than the microinstruction for JSR, because you're simply taking the full 16-bit address in the base register and moving into the program counter after the program counter has been moved to R7. You've already seen the return inside of the trap routines. And now's the point where we'll start talking about the similarities of trap routines and subroutines. Let me just bring to your attention that there's going to be certain tasks that you're going to perform moving forward in the class that will require some custom I/O routines. But just recall, because of the LC3, we can go and find in. We can find the code for in. We know its starting address, and we can find the return, which is a jump R7, gets us back to the calling routine, just like the trap, or just like subroutines. So you can now go in and look at all of those trap routines, and you could, in essence, copy them or move them into user space and make some slight changes. Maybe the prompt, the string Z, needs to be different. But don't make this harder than it really is. There's going to be assignments moving forward where I'm going to specify certain prompts, but those prompts are going to be part of a routine that looks and feels like in, right? But just has some slight differences. Don't reinvent the wheel. Here's our first example of a subroutine and a sample call of that subroutine. This is about as basic as you can get. We would identify the subroutine with a label, and the label is toSComp. And all this does is negates the value in R0. So in this example, the argument passed to the subroutine needs to be in R0. And the return, so think about a function that returns a value, has one argument and returns a value. The return will also be in R0. So we need to save the value in R0 if we're going to need it later. So all we do, and I'm looking at the subroutine definition, we not R0 and store it back in itself. Okay, so we flip the bits. And then we add 1 to R0 and store it back in itself, thus creating the two's complement negative of the value in R0. So below we have the call to the two's complement subroutine. So in this example, you see the comment, we need to compute R1 minus R3, the value in register 1 minus the value in register 3. So we don't have a subtract opcode, so we simply negate the value stored in R3 and we add it to R1. So we move R3 using add R3 #0 to R0. So we're moving the argument to R0. Then we're using JSR. Now we're assuming that the code for JSR is within 1024 instructions. There's that value I couldn't remember. That's the leash or the limit of the 11-bit offset. Otherwise, we'd have to use JSRR. But in this case, we call JSR, and it knows that the argument is in R0. It negates it, and then we simply add the value in R0 to R1 and store it in R4 to complete the original goal of subtracting R3 from R1 and storing it at R4. Take a close look at this. It has all of the aspects of the subroutine, the definition, the argument, location. In this case, it only has one argument, but we could have multiple arguments easily. They would have to be in registers. And we also have the return value. Now, it's worth saying again, if R0 had a value that needed to be preserved beyond this, you would need to preserve it before calling this subroutine. So let's drill down on some important concepts, topics that I mentioned in the previous slide. Arguments are values passed to a subroutine, okay? In 2's complement, R0 is the number to be negated. In the out service routine, R0 is the character to be printed. Inputs, R0 is an argument passed that represents the address of a string to be printed, okay? Return values are passed out of a subroutine or calculated by a subroutine, okay? In the 2's complement, excuse me, 2's complement subroutine, the negated value is returned in R0. In get C, service routine, the character read from the keyboard is returned in R0. Now, you're probably thinking R0 is used frequently. Is this the only return, or the only register we can use as a return? Absolutely not. Absolutely not. Your subroutines are your subroutines, and you could have return values and arguments in any of the 7 registers. In order for a programmer to use a subroutine, the programmer needs to know the address of the beginning of the first instruction of the subroutine, or a label that's bound to its address, the function that the subroutine performs. And here we talk about abstraction. The programmer does not need to know how the subroutine performs the function. Just what changes are visible in the machine's state, sorry, machine state after the routine has run, okay? The documentation for the subroutine should include a description of the arguments and where that data needs to be an argument passed to the subroutine, and the description of the return value and where it is located. Saving and restoring registers is a concern, just as it is with the service routines and R7 and R0. So, and since subroutines are just like service routines, except that they live in user space, we need to save and restore registers if they're needed. So we generally use the call save strategy, except for the return values, okay? And we'll get to that in a second. So save anything that the subroutine is going to alter that shouldn't be visible when the subroutine returns. And it's good practice to restore incoming arguments to their original values unless they're overwritten by the return value. Now, in the examples we've seen so far, they use R0 for the return and also for this single argument. That is not standard procedure. That is not the way you have to do it. It just happens to be the examples that we've seen so far. And excuse me, if you call any other subroutine or service routine from within your subroutine, you must save R7, okay? You must save R7 before anything else is called, any other subroutine or trap routine, and then right before the return in your subroutine, you have to restore R7. Otherwise, you will have broken the linkage back to the calling program. We're going to finish this. I'm going to leave this algorithm here for you to analyze. I don't want to give you too much information, but this is a very useful piece of the puzzle for you, and it shows you all the necessary steps in order to write count-char. Take a close look. And I'm also going to leave the first char algorithm here for you to take a look at. This is a very useful piece of the puzzle for the count-char subroutine project. The last topic we're going to cover is library routines. Vendors may provide object files, not source files, object files containing useful subroutines or functions, and this is done extensively in every high-level programming language you've ever been exposed to. And you'll see in, for example, C++, which at the time I'm recording this, the structured programming in C++ is a prerequisite for this course, then you're going to have the #include library directives where you have code that gets linked, object code that gets linked to the object code created by the compiler prior to creating the final machine language program, the .exe. So this is done because the user doesn't get access to the source code, intellectual property, copyright, etc. So the assembler and linker must support external symbols, or starting addresses of routines to be supplied by the user. So in this case, we would use JSRR because we don't know whether square root is within 1024 instructions of the code as it's being created by the linker and assembler. So this is just one slide to give you an idea of how linking is done. And that's the end of this lecture for Chapter 9. Hope you enjoyed it. Of course, if you have any questions, don't hesitate to reach out to me. Thanks for watching. Have a great day.